Hey guys, this lesson is the first part of 7.3. We're going to talk about logarithmic and exponential form, and it's really your first intro into what a logarithm is. So first, let's talk about what's called a common logarithm. So a common logarithm is a logarithm that has a base, which is indicated by a little subscript number here, a base 10. So inside of that logarithm, it could have a whole bunch of things, but typically, for our examples, we'll just put an x. Now, the other thing I want to show you is on your calculator, you have a button for the common logarithm. Oops, I don't have the calculator open. Let's try that. And I think if you look around the calculator on your own, you'll probably find it. It's pretty obvious once you think about it. It looks like log. Oops, clear. So, over here on the left side says log, L-O-G, that is the common logarithm. You'll notice right above it is a 10 to the x power. We'll talk more about that later on. That is a common logarithm. Common log is base 10. That is my email, okay. So the natural logarithm would be a logarithm of base e. Now you still can write the abbreviation for log, put a little e, which is a number that we learned in our application lesson. Another way of saying the natural logarithm is a logarithm base e is they literally have an abbreviation for it, and it's not what you think. It's ln, okay? So ln of x is another way of saying natural logarithm, and I know a good question is probably why is it not nl, and I don't really have an answer for it. The closest I've come to finding the answer to this is it's a derivation of math from the French community from a long time ago. So I think the translation to natural logarithm in French starts with an L, apparently. All right, moving along. Let's take a look at what's called logarithmic form versus what's exponential form. So logarithmic form, you will have the symbol for logarithm, and then in the little subscript position, you'll have a base. So for the general form, we'll just call it b. Now notice my color usage. If you have colors of your own, you want to use different colors here. Okay, so log base b, that tells you what kind of logarithm it is. And then inside of that logarithm, you have a number. And you can call it whatever you want. I'm going to call it n, and I'm going to use green for that. Okay. So this logarithm will equal some form of an answer, which I'm going to call a, because I'm very clever like that. All right, this is logarithmic form. What we're going to learn in a minute is that our brain does not work in logarithmic form very well, but it can be translated to what's called exponential form using those same vocabulary terms and these same colors. And the exponential form starts with base b. So whatever the base is in the logarithm, that is also our base in our exponential form. Now, what's kind of interesting is the way I remember it is once I figure out who the base is, that's easy, because then the next two numbers are just going to flip-flop. So the n and the a are just going to switch. Let me show you what I mean by that. Now it's b to some power. It's going to be to the a power, and it's going to equal what was originally inside of the logarithm, which is an n. So I purposely chose colors, and I use them with the exact same variable so we can kind of see where they came from. So the trick is to identify who the base is, and then the other two numbers are just going to flip-flop. So for some reason, it's a lot easier for me to go from log form to exponential form. I don't know why, it just is. So looking at the logarithm, you figure out who is your base. Well, the base is a 4. So we're going to write down 4. And then remember the next two things just kind of flip-flop. So these are just going to switch. Kind of. One's going to become an exponent. That makes it a little confusing, doesn't it? So this answer of 16 becomes an exponent of 16. And then what was originally in the logarithm, which is an x, will become the answer. Okay, so see how that worked? You don't have to understand why it works. It's actually way more complicated than what we're ready for. Just know that this is how you can transform from one form to the other. So here we have a natural logarithm of 5 equals 10. So one thing I want to remind you of is that the natural logarithm is really a logarithm of base e. So this really says logarithm base e of 5 equals 10. So when I say who's your base, you're going to say it's base e. Now if you remembered that without having to rewrite it, that's awesome. So now my answer of 10 becomes my exponent of 10. And then what was originally inside of the logarithm is now my answer. So that's going from log form to exponential form. What if we had to reverse that? So for me, this is hard. I have to first remember to write down the symbol for logarithm. And then just like in the other way, I have to first identify who the base is. Well, the base in this problem is a 5. So he becomes the base of my logarithm. Make sure it's a tiny subscript and it's little and it's low. Now, inside of the logarithm is what is the answer to the exponential. So that is now in the logarithm. And then the exponent is the answer to the logarithm. How horribly confusing, okay? So the idea is still the same. Identify who the base is, and then somehow in your brain just remember that these two things are going to flip-flop the order in which they appear in the problem. So instead of xy, it'll be yx. That's the best way I can come up to help you guys memorize how this works out. All right, this next part. Again, I have to remember to write down the symbol for logarithm. And I say, who is my base? Let's identify who our base is. Our base is 10. Then, remember, we're just going to kind of flip-flop the order that these appear. So what is inside the logarithm is the answer to this question. So the x plus 1 is going to be inside of our logarithm because it's got more than one term. I think what I'll do is I'll use parentheses. That way my reader isn't confused. And then the exponent to the exponential question is the answer to the logarithm question. Ha! How horribly confusing. Now, one thing I forgot to mention in the previous slide. A log base 10 can just be written as a log. Because anytime you just see log, like the button log on your calculator, we assume it's base 10. Just like when we see natural log, we assume it's base e. So I really should have wrote that here. My bad. All right. That is probably clear as mud. Here's the good news. They don't change the pattern ever. You just got to practice them a whole bunch, and it's one of those like muscle memory moments in math where the more you go from one form to the other, the easier they become for you. Okay, so now we're going to evaluate a few things, and we're going to try to do this without a calculator. I think we can. All right, so I want to know what this equals. Unfortunately, my brain does not think like a logarithm. My brain thinks like an exponential problem. So what we're going to do is we're going to rewrite all of these in that exponential form. So remember, it's base to the answer equals the number. If I can get it to look like this form, then my brain will be able to figure it out. So in this question, your base is a 3. And then this is kind of interesting. The answer to the logarithm is actually the question. Wow, that was deep, okay? So 3 to what power is going to equal the 81, the number that's in the logarithm? Okay, so this is where you can either think really deeply about powers, or maybe you can use that chart that we gave you last semester, or if all else fails, bust out the calculator and start typing in 3 to some various powers. Don't go too big because powers get really big really fast. So like 3 to the 3rd is 27, that's not big enough, but 3 to the 4th, that's 81. So the answer to this question is actually the number 4. So you rewrite it as an exponential, so that way we can think about it. Because I don't know about you guys, but logarithms are a big mystery to me as far as like what they mean. All right, same idea here. We're going to say, what does this equal? So when I go to rewrite it in my brain-friendly notation, I say, who's your base? Well, your base is a 5. And then the answer is now the power. So 5 to what power is going to give us a 1? Well, that one you might have to think about a little bit. There is a power where when you raise it to that power, the answer always comes out to a 1, and that answer is 0. All right, next question here. I want to know what the answer is. So I got to first change it to a brain-friendly exponential problem. So 4 is my base. I don't like that kind of 4. I'm going to write it like this. And the answer is the question. I don't know. I really like that. The answer is the question. It's very deep. And then inside of the logarithm is another 4. So think, think, think. 4 to what power gives me a 4? Well, that power has to be a 1. All right, now for the ultimate question. It's the last one, so it's got to be a good one, right? Well, the base is a 1/2. And he's being raised to some mysterious power. I don't know it. and it's going to come out to an answer of 8. Well, what would take a fraction, like a 1/2, and flip it so that it's a whole number? Well, one thing I can tell you for sure is that power better be negative, because that's what's going to flip it around, right? So if I decided it's a negative, that would flip it to a 2. So then 2 to what power would give me an 8, and after I think about that for a minute, it comes out to a 3. Don't believe me? Go type that in your calculator. 1/2 in parentheses to the -3rd power, it is totally an 8. All right, that's crazy. They love those questions on no calculator SAT tests because they want to see if you understand the format. So good luck. Okay, so now these next few questions, not all of them can be done with your brain. Some are just too hard to think about. So like for instance here, this is a base 10. So it's like 10 to what power is a 5? Well, that is not a pretty answer. It's not anything my brain can handle. So we're just going to use our technology because remember your calculator has these 2 buttons. So we're going to use our calculator and we're going to type in first the common log of 5. So make sure you're typing the right button here. This is a common log. And then this one here is a natural log. Now one thing I want to make real clear, guys, that is an ln, okay? An L followed by an N. A lot of kids tell me that is IN, which is not anything in math, and that's really embarrassing if you go on to college and you say the wrong thing. All right, so common log of 5, I'm going to use the common log and then 5. And then I already forgot the other problem. It was natural log of 5. Now these should not be the same answer because it's 2 different base logarithms. And they are not the same answer. So common log is, let's round to the thousands. So 0.699. And then 1, I already forgot. Okay, 0.699. And then the natural log was 1.609. So sometimes you just have to use technology. These answers aren't all going to be nice, and that's unfortunate. All right, here's a nice little science connection for you, and I think now is a good time of year to think about all the vacations we want to take. So the slope of a beach is related to the average sand particle diameter. So depending on the size of the sand particles, it either creates a safe beach or an unsafe beach, and erosion becomes a thing, where like it's no longer safe to have people out on the beach. So this is actually a thing where someone would come in and they would test the sand particles and measure them. And they have a certain amount of they have a specification, I guess, for the slope of the beach. Like it has to be between this value. And if it's not, then they have to either make adjustments to the beach, either bring in sand or I don't know what they do exactly, but they have to change it. Otherwise it's not safe. And like someone could be standing on the beach and a big wave comes by, or tide, I guess, and swoop, all of a sudden the beach is no longer there. And this child gets swept out into the ocean, which obviously would be horrible. So this is the formula. So a new friend here that we might notice here is the common log. And there's actually a ton of applications in math and in science, well, in science, using the math common logs and natural logs. Tons of applications, guys. I'm talking tons. And it's kind of kooky that so many things in nature behave in a logarithmic pattern. But this one's not too bad. It just says, well, we went to the beach and we found out that the average sand diameter is 0.25 millimeters. So what we're going to do is we're going to type that in our calculator because no one wants to hand calculate this. So in our home screen, 0.118 times the common log of 0.25. And that would just, I'm going to remember that. Come on, this is where I need kids. 0.149. Let's be honest, I need you guys all the time when I'm giving lessons. I can't imagine how many times I screw up. 118 log 0.25. You don't really need the multiplication symbol there, but never hurts. All right, so unfortunately, I don't know if this is a safe beach or not. 0.078. We'll write that down. 0.078. So they have some sort of a threshold where it says if it's this, then we're good. You can open your beach, and if not, you're gonna have to close your beach down. So imagine being a hotel owner, and someone comes in and says, "Hey, it's not safe. You got to close your beach down." And I'm a hotel in Florida. Yeah, people are gonna be real angry. So that is something they have to monitor. All right, new concept: having to do with logarithms, there's something called inverse properties of logarithms, and this is a good segue into a couple lessons from now where we use properties of logs and eventually solve with logs. So if you have a logarithm and the bases match, so you have log base b, and then inside of it is b to the x power. So you have a logarithm with an exponential kind of embedded into each other. These just end up canceling each other out. So as long as the bases match, they will cancel each other out, and then the x just drops down and it ends up being an x. Okay, simple as that. Now on the flip side of that, if you have an exponential that has a logarithm into its exponent, so they're kind of embedded in each other again, these will cancel out, and the x just drops down, and your answer ends up being an x. Okay, this seems complicated, but it's really nice. Watch this. Log base 6, and then inside of that we have 6 to the third power. Well, these will end up just canceling each other out. So then the 3 drops down, and your answer is just simply a 3. There's nothing holding the 3 up anymore. It just drops down, and it's the number 3. So similarly here, we have 5 log base 5 of x. The 5 log base 5 will cancel each other out. X drops down. Your answer is x. Okay, be careful here. We have base e, which is the number e, and then you have a natural logarithm. So remember, natural log is a logarithm of base e. So this is another case where they will cancel. The x has nowhere to go but drop down. The answer is x. All right, this one always gives kids a run for their money. Now, the 5 is kind of like a separate piece of the problem. Ignore that for a minute. Let's look at just this. Well, we have another case of natural log embedded with an e. The natural log and e will cancel each other out. Now be careful here. There is still a 2. The 2 is no longer in the exponent, right? It's dropping down. So this problem becomes a 5 times 2. So that's why this problem ends up simplifying to a 10. That one tricks a lot of kids because they think it's 5 squared. It's 5 times 2. The 2 drops down. All right, and then here, remember, this is a common logarithm. So there is a secret base 10 right there. So we're going to have that log base 10 and 10 canceling each other. And then the 2 drops down, and the answer is 2. This is going to be a really big, significant part of our lesson coming up when we're solving. So let's keep that in our back pocket for now. All right, one more idea about inverses. I'm going to show you the long way how to find inverses, and then I'll help you with the shortcut, okay? So, actually, you know what? I don't think I'm going to show you the long way today. It's 2020, man. We all need a shortcut these days. The inverse of a logarithmic function is just his exponential buddy, okay? That's it. So for the ones we're doing in Algebra 2, they're very simple. So I'm going to just write down a general form here. So if you have a logarithm, right? Logarithm of base b. His inverse, which I'll call y inverse like this, is just going to be an exponential of base b. So the inverse to a logarithm is an exponential. The inverse to an exponential is a logarithm. That's the next section. All right, so here's this function, y equals log base 3 of x. Well, if I want to know his inverse, first thing I'm going to do is I'm going to call it y inverse. The base is the key. So it's a base 3 and then to the x power. So all I had to do was create an exponential that has the same base as the logarithm. This works for the simple ones like we're going to do in Algebra 2. If you move on to pre-calc, there might be a little more work because maybe there's some transformations where that gets kind of crazy, but that's not a big deal. All right, so the inverse here of a log, this is a common log, right? Write myself a little note. This is a common log. So his inverse would be an exponential of, remember common log is a base 10. So it would be 10 to the x power. And that's it. I know, seems like there's a catch, right? All right, so flip side of that. If the inverse to a log was an exponential, then the inverse of an exponential would be a log. So the inverse of 4 to the x power would be a logarithm of that exact same base. So this guy has a base of 4, which means my logarithm has a base of 4. But don't forget to put something in the logarithm. You need an x. No, don't get tricked by this one. The inverse of an exponential base e. So you can do a couple of things. You can either write logarithm of base e, because that's the base, right? Log base e of x. Or a better way to say log base e is to call it our natural logarithm. I technically like both those answers, but the more common notation would be to use the natural logarithm. Plus it's less letters and less writing, so it's better. That's what I say. Okay, so that was your very rough intro into logarithms and what they are. Our next lesson is graphing a logarithm, so you can kind of see what a log looks like and how it relates to the exponential function. Good luck, everybody.